All right, good morning, class. Look, we made it to the end. This was a crazy, I wouldn't say crazy, but it was a quick 5 weeks. I don't know if y'all felt that way, but as I mentioned at the beginning of this class, this is one of those things that like start off feeling very manageable, and the next thing you know, it's like in the stratosphere. So I trust and hope everybody on here and that's watching this has been able to manage to some extent. And this is what we're going to do today. I have sent out the final exam review that just kind of lets you know how many problems, what each problem is going to be over. What I'm going to do is conceptually go through that. I'm going to conceptually go through that just in terms of reminding you, what concepts you need to cover. If you want to have a example problem to work through, there are going to be example problems, or they're going to be problems identical to what you've seen on the homework. It's not going to be the hardest one in the chapter, nor would it be the easiest one in the chapter. But in that particular chapter, when you had a homework assignment, the example problems would be very, very similar to that. In fact, it may even be something very identical, very much identical to what you've seen on your homework. So we're going to go through that. And then if we get to a concept, for people who are here live, if we get to a concept that you want to ask a question on, raise your hand, and then I can kind of give a little bit more explanation on that particular concept. Cool. Give me a thumbs up if y'all good. Since I got to hear for feedback, thumbs up. Duncan is good. All right. People who don't have the camera on, there we go. Aiden, Preacher, Reese, appreciate you, y'all. All right. Thank y'all so much. Have you been able to see? I'm gonna share my screen. Have y'all been able to see this final exam review? Has everyone been able to see that? All right. It should be in your inbox. I sent out an email very early this morning. And you see on this, when you open it up for this final exam study guide, the exam will have 9 problems, right? Each problem obviously won't be in the exact same order that you see here, but there are going to be 9 problems, and each problem is going to be worth 10 points. And the topics of each problem will be as follows. So you all, I encourage you to open this on your computer, wherever you're watching this, so you can follow along. I'm just showing it real quick so you can see it. 9 problems, got the final exam time. Make sure you keep note of that. Do not lose track of that time so that you can avoid having to send that email about trying to take it over, which there are no guarantees will be possible. So make sure you make that time. Make sure you make whatever arrangements you need to make for your job, whatever the case may be. All right. So let's start things off from the jump. Again, y'all are more than welcome to ask questions as we get through this. But the first problem, change my view here, come to document camera. The first problem is going to be on chapters 1 through 3. And the reason why I say 1 through 3 is because a lot of these kind of merge into each other. And at the end of the day, what you're doing in chapters 1 through 3 is just trying to find the elongation of either a bar or a wire. And you just want to remember that delta L over L, that's equal to strain, right? You want to be able to remember that relationship. You also want to remember the basic equation that stress is basically force over A. Keep that in mind. Sometimes, depending on the shape of whatever is stretching, you want to make sure you remember the area. If it's a circular area, right? Pi r squared if it's circular, or base times height, right? Keep that in mind. And what you'll probably be given is, let's just say, some sort of setup where maybe you have a distributed load. Maybe let's say this is fixed. This is distributed load, and then there maybe is a wire here that's holding it. Right? So you want to try to find out, in this case, if you were given something like that, what is the force in the wire? What is the area in the wire? You can take that force, place it over the area, get the stress. Perhaps you will be given a problem where instead of finding the stress, you find a displacement, right? What type of displacement is in the wire? You can take that displacement, put it over the area, find the strain. And then lastly, of course, we know the relationship between stress and strain, sigma equals E epsilon, right? Basic concepts from chapters 1 through 3 to keep in mind. Again, if you want to do some example problems, I encourage you to go back through your homework problems. They're available for you for this particular chapter. Make sure that you understand them. You have all the solutions to them. You can just go back through them and make sure you understand them quickly on your own piece of paper. Time yourself, see if you can do it in like 15 minutes or so, because these particular problems should be the easiest of them all. All right, good with that? All right, cool. Let's keep it moving. The next problem. So let me say this is chapters 1 through 3. Again, in no particular order will be these problems, 9 problems in total. But the next one is chapter 4 will have its own problem. And so this is stress, strain, and deflection of axially loaded members. Stress, strain, and deflection of axially loaded members. Another very simple concept. Axially loaded members ultimately came down to like bars that may have been fixed on one side. And your job may be, and let me make sure, look like we have a question in the chat. Mood session mission says the exam starts at 8 a.m. and 3 hours on syllabus 8:30. Good question. Thank you so much, Reese. Matter of fact, raise your hand if you get a question, just so I can make sure I notice that is in there. Question is asked about the length of the exam. Yes, based on the university, it should start at 8:30. So that will be changed. So that means that it should be 2.5 hours long. And that is what the test is designed to be able to be completed in. In fact, it's designed to be able to be completed within an hour and a half. So with that being said, you will have plenty of time to make sure you can fill everything out. But yeah, we'll make sure that the time is in line with the university's time for the exam. All right. So number 4, back to chapter 4, one problem is going to say, maybe it'll give you a force here. Let's just say this is 10 kilonewtons. Perhaps there may be a point in the middle that gives you another force. 5 kilonewtons. And keep in mind that something like this can be in any direction. It can be coming down. Right? It could even have a force that's being applied at an angle here. What you would do in that case, if you would determine that this is what kind of angle this is and get the axial component of it. Right? So if this is a 3, 4, 5, 3, 4, 5 triangle, and let's just say this is angle, this is a force P. Well, the axial component of it will be 3/5P, right? So at the end of the day, you're going to make sure you understand what forces are actually being applied to this beam. And then what you're also going to need to do is use this equation right here. Delta equals PL over AE. PL over AE. That's going to be your bread and butter. Any thoughts or questions on chapter 4? I think you all will be able to figure that one out too. Stress and strain of deflection and axially loaded members. Thumbs up if we're good to go. Thumbs up if we're good to go. Again, we're going conceptually. If we need more clarity on any of these concepts, make sure you ask the question so I can slow down. All right, cool. Thank you so much for the thumbs up. Next, you're going to need to make sure you understand how to do a problem out of chapter 5, which is shearing stress, strain, rotations, and torsion. Shearing stress, strains, rotation, and torsion. So very similar to the axially loaded members. What we need to do in this case is just remember that a bar could be going in any direction. If I can draw something for you. Right, so a bar could be going in any direction. Let me start off here again, right? And let's just say that it's fixed on this side. And you may be given some applied torques here, right? And these are moments. So this one might be, say, 100 kip foot. This one might be, I don't know, 50 kip foot. Kind of using the same ratio I had up here. Right? And then you may be asked to solve for any measure of things, right? It could tell you that, hey, this is also a hollow tube, which is going to change the way that it's being applied. And what you should be able to solve and interchange is equations such as this shear stress, if y'all remember this one, tau equals TC over J. Remember, J is the polar moment of inertia. And that changes depending on whether or not this is hollow or this is solid. Or you may be in a situation where we're talking about statically indeterminate, and you're going to have to determine what is the internal torque that allows you to then solve for this angle of twist. It's going to be TL over JG. Equations that involve both of these or problems that involve both of these equations are the ones you want to be very familiar with. I would say for this particular one, just to give you, I guess, a little bit more tip, is that it will probably be a determinate, not indeterminate, but a determinate problem. But nevertheless, remember, this angle of twist is not the same across. You may have, let's just say this is point A, this is B, this is C. Remember that the angle of twist in this point, A with respect to B, is not necessarily the same thing as the angle of twist of B with respect to C, or A with respect to C. So make sure you remember if you need to add those up, depending on what they're asking you for. But I can go ahead and give you the, I guess, the tip that it's going to be a determinant, meaning you will not have to in this particular problem. I'm not saying that for chapter 4, but in this particular problem, you will be able to solve it without worrying about, your boundary conditions or anything of that nature. Cool. All right. Let's keep it moving. That is chapter 5. We'll go to another page. The next problem is going to likely be over a concept found in chapter 6. This is where I think some people may have begun to have just a few issues. Let's see, 4, chapter 6. This has to do with bending in beams or design of beams. And it may be determining the shear force, bending moment in their diagram. So there are a couple of things that were relevant to this particular chapter, right? What was relevant was, first of all, you had, let's say, a cross section. So you have an I-beam here. And in this particular chapter, we introduced you to the fact that there is a shear that's happening parallel with this surface. These are little arrows that I'm drawing right here. Right. And then we also share with you that there is a shear flow that happens longitudinally, particularly at these interfaces here. And so we told you about the fact that there are fasteners at times that go through this interface, and that you will have a need to be able to calculate that, that shear flow, or calculate the shear stresses on that cross section. I'm going to turn to the chapter real quick so I can draw something. All right, so here you have flexure formulas that you dealt with. So you do want to remember that your shear stress, not your shear stress, but this flexure formula of M, Y, or C, right, over I. You want to keep that equation in your toolbox for this particular problem. You also want to remember, let me make sure, I just want to make sure I write this particular equation correct. The fastener equation. Give me 1 second here. While I'm looking for that, of course, you want to remember that it's important to be able to calculate Y bar for this equation, right? Summation of AY over summation of A to find the neutral axis. Very, very important to locate neutral axis. And then this is the equation where it's very crucial to know how to solve for I. There are a couple of ways, again, where you can solve for it by, taking the base times height over the entire thing and then subtracting base on height cubed over the gaps minus the gaps. Or there's another way you can solve for it where, I hope you all can see this well, and feel free to, again, to come off mute if you just want to say something. And then there's the other one where a lot of people were curious about, not a lot of people, just a few people, where you would use the summation of the equations, BH cubed over 12 plus AY squared. And just to give you an idea of when you use one over the other, this one can be done only when it's a symmetrical shape. So if it's the same height, it's the same thickness, everything's the same, and it's basically like a big rectangle, and then the gaps you're going to take out are also symmetrical. They all share the same neutral axis, essentially. You can use that. This is the one you're going to need to do when you're unsymmetrical, because this Y right here takes into account the fact that not all components of it is going to be sharing the same neutral axis. So make sure you do some practice on that. And then I just want to make sure I give you this one more equation here. Am I in the right one? This is chapter 6. Okay, maybe this is that. Maybe it's just in the next problem. The equation I'm looking for is in the next chapter. Yep, absolutely is. Absolutely is. All right, so here's basically what you need for chapter 6. Make sure you can calculate this. Another thing to remember is for chapter 6 is that, if you're looking at a cross section here, and it asks you to find the force on the top board. Let's say that's the top flange. This is the web, and this is the bottom flange. And you keep it in mind that, hey, here at the top of this, we have this distribution of forces. If you know that this is the stress, remember the force on the top board, which it could ask you, is equal to the stress on the top board times the area of the top board, the top flange. So make sure you keep that in mind as well for chapter 6. So I almost started to combine when I started to talk about the stress here with what is going to be on the next type of problem from chapter 7. Chapter 7 is where we're going to get into the fasteners, the shear stress and the fasteners. All right, and this is where we dealt with everybody's favorite concept. I only say that because it's weird, but it's definitely one of those things that you can figure out once you kind of get a hang of it. We're still going to need to know how to calculate y. We're still going to have to be proficient in calculating the moment of inertia. But we're also going to deal with this equation right here. Tau is equal to VQ over IT. And again, if you're here live, I do encourage your questions here. Let me see if anybody else coming in. All right, I do encourage your questions here if you're having a hard time understanding this. So tau is VQ over IT. Q is what I said is everybody's favorite because it's one of those terms that you aren't able to visualize always, but once you use it a couple of times, you can get more comfortable with what it is. Another equation here is the shear flow, which is little q equal to VQ over I without the T. Right? And then lastly, if you're dealing with fasteners, the force in a fastener, F, is equal to little q S. So no one has asked this, but I'm going to go ahead and explain this when it comes to Q, because sometimes you are going to be using the entire area. Let me just use something very simple, right? A rectangular I-beam. This is NA. And let's just say this rectangular I-beam has some fasteners right here. It's an interface there and some fasteners right here. Well, if you have to find out tau max, the maximum shear stress, well, then in that case, you're going to be doing Q max. And Q max is the entire area above the neutral axis. That's Q max. However, if the question is asking you to just find the shear stress of everything above a certain point of interest, in that case, the Q is just going to be the Q of everything above that particular point of interest. Does that make sense? When to use Q max and when to use everything above the neutral axis versus when just to use everything above the interface? I want to see some thumbs up for that. Thank you. Duncan, appreciate it. Anybody else?
I have a question about that. No.
Mhm.
So So if the point of interest is just at the bottom of that area that you marked as for the Qmax just now, right? Then we take the Q of everything above that. If we're given like a point, like point E or something like that.
Right. You could be given a point here.
Yeah.
Yeah, like you said, point E.
Are
But
we
when you say
ever
the
gonna,
bottom,
is Q ever gonna be the area below that?
no,
Or
it's going to be area
yeah.
beyond the point of interest. So if you, let's
Okay.
just say if it's on this side, the reason why I use beyond it specifically is because if there is an interface here, then it would be the area beyond that in that direction. So no.
And yeah, and my other question is for an asymmetrical shape, would it be like maybe asymmetrical on one axis but not the other kind of thing, like a T-shaped area?
So asymmetrical meaning like the top flange is wider than the bottom flange.
Yeah.
Uh-huh.
How would we go about finding Q, like, or Q for finding Tmax? Like, is it gonna be on the shorter side, or does it matter? I imagine it matters.
Yes. So you're saying like, okay, if you want to know the maximum for here or here.
Yeah.
So if the point of interest is here, right? If you have fasteners here, and let me think of how the question could be asked. It could be asked something like, all right, what's the maximum allowable spacing? Right?
Yeah.
Because you got spacing here and you got spacing here at different nails. And they're going to be experiencing two different shear flows, right? So in this case, Reese, you're going to have to do both of them and see which one gives you the controlling one.
Yeah.
So you're gonna, yeah.
I'm one thing, or I guess it would be easy to just practice with it, but which one, or but for this one, because like the Y bar is going to be closer to the top, would the higher shear be on the top or the bottom?
The
Or
higher shear?
yeah, or the the decreased nail spacing and all that.
Well, I just want to put it out there that there are ways you can kind of maybe assume, but I just want to put it out there if you want to do both of them, right? So you would do this equation here for both of them, and then you would take the higher shear, right? The higher value here.
Yeah.
First, you take your higher value, you take your both values here for your Q. Then you'll be able to calculate two different shear values.
Yeah.
Or even you'll be able to calculate this, scratch that, you can calculate two different shear flow values. You use your little Q then to come over here and solve for your spacing. And so if the question, as I just gave you, is asking for your maximum spacing, the answer would be whichever one gives the lowest number of S, because that's the controlling one. Is that helping you out, your question, or did you have another one?
No, it makes sense.
Okay. So the answer is to do both though. Like I don't want to say, oh, just assume it's going to be the smaller one or the bigger one. Just do both of them and then compare and determine which one is controlling. Cool?
Yeah.
All right. Any other questions on this one, chapter 7? Again, just to clarify, I was cramming an extra. I was thinking more would be involved in this chapter 6. Chapter 6, you want to be able to utilize this flexion formula really well. Find Y bar, find I. Chapter 7, you want to be able to also still continue to be very proficient with the Y bar and the I, but these are the equations that you're now going to be utilizing in this case. Shear stress, shear flow, and then your fasteners. All right, let's keep it moving. So that's chapter 7, problem 5. Again, in no particular order, we're going to talk about chapter 6. I mean, not chapter 6, problem 6, which will likely be a problem on chapter 8. And when it comes to chapter 8 is solving for reactions. I'm sorry, solving combined stress. Oh, never mind. Chapter 8 was the simple one. That's the one we did, had one problem on, one homework on, rather. And I hope that you all were able to, really pick that up fairly quickly. But that's combined loading. Just a few days ago, we talked about this one. Excuse me, I'm sorry. So you have your stress is basically equal to a combination of your axial stress plus or minus your flexural stress. This was, again, quite straightforward in order to explain. Let's just say we had a bar sticking out of the ground like this. And the force, the axial load, we know that this is the neutral axis here in both directions. But the axial load is over here. And it's going up. Well, first of all, we know that here it's a positive. We're going to basically take that P and we're going to put it over the area of this entire cross section, because that's going to give us the axial stress. And then, depending on where we're trying to solve it at, let's just say we're trying to solve it here. We have to look at the fact that this axial load is located at a certain distance from the neutral axis. We call it eccentricity. So that means that it is creating a moment about the neutral axis, which means that on one side, it will be creating a positive stress, but because of the moment on this side, it's going to be creating a negative stress. So the way that we will write the moment in this case would be P times E, or times the distance from the neutral axis. And there we have a force times the distance. And then Y in this case, if we're asked about this particular point, if we're asked about that particular point, Y in this case would be the distance from the neutral axis to that particular point. So I'll just put Y right there. And then I is, of course, moment of inertia. Now answer this for me, just to make sure I was, you can put it in the chat. Would this be now a positive or a negative if we're combining these two loadings to find out what's happening here? Will we be subtracting this term or adding this term? Boom, negative, love it, because it'll be a compressive force at that point. So you just want to make sure you are able to always determine, which is really not that difficult, what's the distance of this force from the neutral axis? And then ultimately, based on what you're trying to solve it for, if we were trying to solve it for this side, right, it will be a positive because it's also adding tension stresses there. Determine whether you're going to be adding those terms or subtracting those terms. Only one other thing that can perhaps make this a tad bit more complicated, and I think you had a problem like this as well, is if they give you a full bar and you're cutting the bar, and you got a moment on this bar as well as a stress. Well, you're going to also have a term where this moment here is going to really just be that internal moment that's at that particular cut. And I believe the problem gave you the cross section here, just to give you an idea of, oh, okay, we want you to find it at that location. I think that was one of the one of the homework problems. So this is just shown just so you'll know that, hey, they're asking for it for a particular distance away from the neutral axis. So that distance is going to inform your Y, right? The point that they wanted at is the Y. So Y is the distance from the neutral axis to the point of interest. And then moment is that internal moment. So it's either created by the internal moment or the fact that this axial load, see, in this case, the axial load isn't eccentric, it's right down the middle. So that's not creating a moment. It's just an internal moment that's going to probably be as a result of, your external loadings or things of that nature. So you'll need to solve for that. But the concept remains the same, combined loadings for chapter 8, the 6th type of problem that you can expect. Any questions on that?
Yes, I have a quick question. I think one of the homework problems briefly touched on this. We're covering normal stresses for these types of problems, but is there anything special we do with shear stresses in this case?
For combined loadings?
Yeah.
No, we won't do any shear stresses for combined loading.
Okay.
Yeah.
Thank you.
Yeah. Good question. Good question. All right. Moving right along. I think. Let's see. Chapter 9. 7th type of question, chapter 9. Moore's circle. So when we did this in class, or when we did this for the lecture, what we share with you is that there are more than one ways to find your stress transformation, your principal stresses. We gave you the equilibrium method. We gave you more the equations. And I know the equations was probably like, appeared to be the most simplistic, but it's one of those things too, where if you plug in the wrong angle, then the whole thing's wrong. It's not a whole lot of room for partially right or partially wrong. And then we gave you Moore's circle. All right, so here's the tip. Here's the spoiler alert, just to get it off. We won't have you draw a Moore's circle on this particular final exam. It just got kind of weird for some people, I guess, drawing it, and some people were actually drawing it correctly, but because the master in engineering thought it was done a little differently, some things were getting wrong. So we won't have you draw a Moore's circle. The equations I told you are kind of straightforward, but it's really not much of a partial credit involved. So I can tell you right now that we're going to be doing the equilibrium method, and it should be a simple one of those. So I'm just going to quickly remind you how we go about determining that from a conceptual standpoint. And the goal is to make sure whatever you see on the exam, you're able to do yourself. All right, so check this out. Let's just say you're given a situation like this. You have some normal stresses coming out the side. I'll go with my convenient 10 KSI coming out this side here. I'll go with my 5 KSI as I've been doing throughout this entire thing. And then you may have some shear stresses here. Shear stresses. I'll call that 15 KSI. But they're asking you to find the stress transformation or the stress components acting on a certain inclined plane. And they give you an angle of, I'll just say 30 degrees. All right. The way you would then go about solving this is now drawing your triangle. Matter of fact, I'm going to do it down here just so we can clearly see what's going on here. Draw that triangle representative of this rotation, 30 degrees. And coming out the side of that, coming out this space is always going to be our new X prime axis. And then parallel to that face will be our will be our y prime axis, but this is also in line with our tau x prime y prime. So here, remember, here's what you got to remember about the equilibrium method. What we're going to be doing is essentially summing the forces. We're going to be summing the forces or the stresses, or whichever one you want to think about it as, whatever it helps you, on along each side. So on this side, we still have this force or the stress of 10 KSI. But you got to remember how this particular stress reorients to be in line with this axis and this axis. So this angle right here is 30 degrees. You guys with me? We still have this 5 KSI coming out of it here. But to reorient it, you're going to have to keep in mind that this angle here and this angle here, or that angle created, is 30 degrees. Just so you can be comfortable changing the orientation of what we were originally given in the problem. The same thing goes for the stress here. And this is just to finish drawing it. And for this shear stress here. And what you're going to be doing in the equilibrium method is remembering how to change or how to gather all of the components in the x prime direction, add it up to solve for what this is ultimately going to give you, sigma x prime, and then all the force, all the stress components in this y prime direction, you're going to sum up and then solve for x prime, y prime. So it would look something like this, just again, conceptually walking you through it without doing an actual problem. You're going to go around here and you need to remember trigonometry to know how you write these particular terms. So let's start with this big triangle. The face, this face right here, is going to be found by doing the sine or cosine of 30. Anybody know? Tori, you got your hand up. Sorry if I'm just not seeing it. Okay, you actually said on one homework question, we actually found a maximum shear and the angle ended up being a negative shear. Should we just find the smallest angle between the extreme? I know I understand the first part of your question, but I don't understand the last part of your question. Should we just find the smallest angle between the extreme? What do you mean by that? You might come on off mute just so I can make sure I understand you. If you're in a place where you can talk, can't speak. Okay. Got you. I don't quite understand the second part of your question. So when you say, should we just find a small angle between the extreme? I don't know what that means, but I would say this, just to save you some care. In this particular problem, since we're doing the equilibrium method, you're probably not going to get too concerned with the angles. Was not positive or negative maximum. Tori, did you catch what I just said? So I would focus for this particular problem, not so much on the angles, but how to solve for this tau x sub x prime y prime times sigma sub x prime using the equilibrium method. So I don't know if that helps, but I'm more than willing to make sure I understand your question, but I don't know if that kind of gives you enough to kind of feel comfortable with moving forward. Okay. All right. Let me keep explaining this. If you want to continue, if you want to revisit it, let me know. But focus, my suggestion would be to focus on solving these with equilibrium method. To go back where I was in the problem, this side right here, this bottom side, is going to be found. So if this face is delta A, right? The hypotenuse is delta A. This space right here is delta A cosine 30. And then this face here is delta A sine 30. And then the same thing is true about these particular components, right? So the component that you're originally given is 5 KSI is your hypotenuse, So that means that this face right here is sine 5 times sine 30. And this face right here, or this component right here, is cosine 30. Realize I'm writing kind of small, but just make sure you can be able to determine if this is your hypotenuse, the way I get this component, it's going to be cosine 30. The way I get this component, it's going to be sine 30. So if I'm summing the forces in the X, or if I'm summing the stresses in the X prime direction, if I'm going in the X prime direction, first thing I'm going to write is the one we're trying to solve for. So a positive sigma X prime. And this would be times delta A. But if you recall, when we talked about this, all the delta A's are going to cancel out. So we won't even write delta A's on any of them. All the delta A's are going to be canceled out. And then in this term right here, if I want to, all right, what type of component is helping it in this direction? I know that this hypotenuse is actually creating a negative. So I'm going to say negative 10 KSI. Well, I don't know how to say KSI, 10 times this face, or this, to make it, this component is going to be times sine 30 times the face that is on. And that's another sine 30. Again, we're not writing the delta A. And then I want to come around here. I'm going to make sure I get all of my components. I'm going to come around here. All right, what component, or how do I write this 5 KSI in line with this X prime direction? Well, I see it's also going to be creating negative. So I'll say minus 5, make it X prime component, 5 cosine of 30 times this face that is on, which is also cosine of 30. And so forth and so on. You're going to go all the way around and make sure you got all of your components, or all of your terms that are going in the X prime direction. And the only unknown when you're done with that, after you set it all equal to 0, should be sigma X prime. And it's just a matter of getting it all into your calculator and solving for that. Then you're going to do the exact same thing when it comes to the tau X prime, Y prime. So I'm going to do these same two terms here just to make sure we're all on the same page. So the first term is that. The second one is, let's come this way first. We're going to say a 5. And because it's going in this direction, it actually would be adding to it. So 5 KSI times the sine of 30 times that face, which is cosine of 30. And then this component over here is actually going that direction. So this is going to be minus 10 times, this is the cosine side. So cosine 30 times that face, which is sine of 30. So forth and so on. Make sure you have every component, set it equal to 0. Then you're going to ultimately solve for tau sub X prime, Y prime. Questions? Everybody good?
I have a couple questions,
Sure.
not specifically about the setup, but about the chapter in general. The first one, there are a couple problems on the homework where we were given a beam or a couple of different beams connected together, pinned together. And we were supposed to find things like the principal stresses and the orientations at a certain cross section in that beam. And I was really uncertain of how to get from the entire beam to this simplified box that we've been using to, draw more circle from which we find all these principal stresses. I was wondering if you might be able to give an example or explain how we get from the larger structure to the simplified structure that we can more easily work with to find these things.
Okay. I'm trying to find a particular problem. Do you have anyone in mind?
I think my problem 4 on I think it's homework 21 was one of the ones that was along these lines. I can check real quick.
Let me see. Chapter 9. See what I assigned you. Okay, so you have some. Let's see. $9.45 is one. But no, that's not one.
This one is 9.73.
Okay, 9.73. Determine the principal stress at D. Okay. And D is in the middle of it. Yep. And then they gave you an angle. All right. Cool. So it's really straightforward, right? So if they give you a beam here, let me come up here. Right. Ultimately, we're trying to get to a place where we look like this, where we know where everything is here. Right. Well, if they give you a beam, and I think in this case, they gave you the angle of 30 degrees, right? They just kind of drew it here. That's the angle they're dealing with. Now, what you're going to do if you find a cut here is that you should be able to find two particular things, right? You should be able to find your flexural stress by taking the internal moment, y, which is the distance from the neutral axis to that D, over I. And then you can also find what we know from earlier in the chapter, your shear stress by taking the V, right? Whatever vertical shear, internal shear force, VQ, right? Q is going to be the point beyond this point of interest. So if you think of it as a cross section, and they gave you that point there, you're going to find Q beyond that point of interest. Are you with me? Over I. See? And so now you have, and once you find this, now you already have your angle. You have everything you need for this particular square. So you could draw this like this. You know, you got an angle of 30 degrees, right? And then your shear stress, your stress coming out on the X side is going to be whatever this value is. So this is going to be sigma X. So just think of this as sigma X. That's going to be your flexural stress. And then it's coming on this side. This is always going to be your sigma Y. But in this case, there is no sigma y, right? So all you have is basically the stress coming out of here. And then you have your shear, which depending on if this is positive or negative, let's just say it's positive. This value here is going to be your tau, whatever that is. So in this case, this will be 0. This will be whatever value that is. And this is going to be whatever value that is. And now you can draw it just like the simplified versions that we've been drawing. Because this side is going to be the equivalent to that side, and this side is going to be equivalent to that side. And all these shear stresses are going to be the same.
Okay, I think I see it. Just to clarify, the internal moment and shear force that you're using is taken from that vertical cross-section, not cross-section at that 30-degree angle.
Right. So if they gave you a full bar, you should be able to find your internal moment at the cut, whatever point they're interested in. And I could have drawn it like this. It's showing the cut.
Mm-hmm.
Yep, wherever moment that is. And then your shear is here. And those are the values you need for that and that. And then you kind of got to imagine this cross section. It looked like they gave it to you. Or they even gave you the cross section when it comes to finding your Q and your distances. So this is definitely a multi-step situation if they were giving you that. And we're going to try to keep it a little bit more simple on the exam, primarily because we know that it's going to take you a little time right here determining your trig functions.
Yeah, thank you. That does wonders for clearing up my confusions on that. I do have one more question though. With the theta sub S and theta sub P, there's a couple problems that ask us to find the quote unquote orientation. I'm not really sure what that orientation is, or like I can solve for it, but I'm not sure of the physical significance of that. I was wondering if you might be able to clarify.
Okay,
that.
Yeah, so that's a conceptual thing. So if you think about the fact that you're going to have an object, a solid, and it's experiencing forces from various directions, right? You want to know if you think about it as a little piece, a little part of that particular solid, experiencing all these forces, there is a certain orientation where the maximum stresses can be thought of as perpendicular to the faces of that. Let's just say the maximum stress is in this direction and that direction. Instead of looking at it as just a block or a square that's just kind of right side up, you're going to basically try to find out what orientation of that block what angle can you make that block at, the little piece at, to where now the maximum stresses are perpendicular to their sides. And that's easier to analyze. So it's a matter of, it's easier to analyze these things where you say, all right, let's find the angle of it, and then let's analyze it as if they're all like normal stresses.
Okay, I see.
You see what I'm saying?
Yeah. All right. Thank you.
Yeah, no problem. No problem. I think that kind of touched on your question, Tori. I don't want to leave you hanging. Later in the chapter, he talked about the shear angle. I think you're talking about how they know if it's positive or negative. That sounds like a more circle question. I'll say this in general, Tori, and I don't want to leave you hanging, but if you're able to maybe come off me for a second, I'll be more than happy to try to revisit it if necessary. If you're good, don't worry about it.
So
But way people draw more circle.
I did find the question. It was 956 and
Say the number again.
956 and
Okay.
I know mine's randomized, but the maximum in plane shear stress was negative 56.6 megapascals. And
Okay.
I was wondering, or when I originally submitted that, I submitted positive 56.6, and the angle was greater than 45, but it was in the opposite direction. So should we just use the maximum in plane shear stress that's closest to the current angle, or like focus on whichever is closer?
So you're talking about like, this is a more circle question. So you're talking about like, if you got something here and you find out your reference point or something like that.
Yeah.
Should you use this angle as opposed to like that angle or something like that?
So
Or this angle?
yeah, the maximum shear stress. Yeah, since it would
Yeah,
be
yeah.
if it's at the top of the circle,
if it's
that would be a
principal,
negative.
yeah, if it's principal, you're going to be using this one.
Okay, but for the shear stress, it would be at the top of the circle. But that would be a negative shear stress. And
Okay, boom. So this is how people write more circle. I don't know who came up with it, but how positive is in this direction.
Yeah, but since it's at the top of the circle, it would be a negative shear stress. And
Right.
when it said to find the maximum, I just went for a positive, and I went the opposite way around. So should we just try to find the closest maximum or the positive maximum?
Yeah, I would say the closest.
Okay.
It's not, they don't have to necessarily think of it as an absolute. Which one is the positive maximum? Yeah, don't think of it like that.
Okay, thanks.
That help?
Yeah.
Okay, cool. All right, let's keep it moving. Let's see. We're getting short of time. All right, so we have 2 more things to do, or 2 more concepts to cover. Chapter 12, problem 8. Shout out to people watching this on replay. This is definitely going to be a longer one, but it's necessary. Necessary if you really want to make sure you are prepared for this final exam. Thank you all for your questions. You all have excellent questions, because I know somebody watching this on replay probably has a similar question. So what we're doing here in chapter 12, you all remember this. This is when we want to find deflection, or let me say the elastic curve, EIV. We need to find the slope equation, EIV prime, or when we're trying to find the moment, which is usually where we start with this whole situation, d squared v over dx. This is usually the moment equation. The way we get that is whatever we're starting out with. Let's just say cantilever beam. Maybe there's a force there. We want to cut it. Yeah, that's the x direction. We're going to cut it. And we're going to solve for this moment right here. Whatever equation, because obviously this one will have a reaction here. Probably have a moment reaction here, or what have you. Whatever this equation gives you when you solve for the moment about the cut, that's going to give you your first equation here. You're going to take the antiderivative to get this equation here, which is probably going to be some term plus C1. And then you're going to take the antiderivative here, will be some term plus C1x plus C2. All right. And then what you're going to then do is find out a boundary condition, which we know that say when x is, if this is fixed on this side, we could say when x is equal to 0, the displacement is also equal to 0. And because this is fixed, for this particular case, because this is fixed, we could also say that when x is equal to 0, the angle is also equal to 0. So then we can set this equation, right? The slope, this is the slope, the angle, and this is the displacement or deflection. They call them different things. They call them displacement. This equation has been called, it's called the displacement, elastic curve, deflection. All those are the same thing. But we would set this equal to set those equal to 0. That would allow us to solve for C1. In this case, we can set that equal to 0 as well. Which should allow us to solve for C2. It's not until we get these values and then we rewrite these values into these equations that we actually have these equations. So right here, we have these equations, but we're just putting these C1 and C2 for a constant. We got to use these boundary conditions to solve for the constants. Now, so if the problem is asking us to write the equations, it's not until we solve for the constants and then rewrite these that we have those equations. Now, after that, they may say, okay, what is the maximum? Well, now that you have your equations, if you had this case, you know that the maximum, let's say displacement, is happening at the end. So now you're going to go back and say, what is the length of this entire thing? What is this L? I'm going to plug in L for X into my actual equation, and that's going to give us the maximum. That's chapter 12. This was another one of those tedious things, but any questions? I want to make sure this conceptually makes sense. All right. All the best on this one. All the best on this one, because I know that at times, oh, the last thing I want to remember, don't forget to divide EI by both sides too when you give your final answer, because EI is placed on this side because it's treated as a constant, just to keep it out of the way of all the calculus that's going on at first. But when you get ready to present your final equation, make sure you have EI divided off of that side and on the other side, and simplify it as much as possible. You have I understand again how it can kind of get a little tricky. It's easy to drop things, but once you kind of get through the algebra and you find your constants, at that point, just make sure you don't drop anything as you simplify. So that's chapter 12. The last thing is chapter 13. And then I have some really short announcements after I go over this. Chapter 13. And that is going to be likely the 9th type of problem. And that was determine the loads, stresses for buckling columns. Another simple one we just did. That's actually the most recent concepts we just did yesterday. In fact, I think you're on a homework assignment right now of that. And just to put that in a nutshell for you, you're going to need to be able to determine, it looked like we got it pretty simple for you. So you want to be able to determine what is the buckling load, right? What is the buckling load? Give me 1 second. Right. So what is the buckling load? We call that P critical. P critical has an equation of pi squared EI over KL. That's the effective length, right? So you're going to want to find this. And then there was something that we talked about in this course, and this is just a little tip again in terms of what you can expect as it relates to what we call the factor of safety. Right. So the factor of safety is basically the load that you're designing for, or the critical load, or how much higher the critical load is over the actual force that it's experiencing. So if the factor of safety is 2, you can set that equal to 2. You can solve that through the equation, and then you can back calculate what is the allowable. So I just want to throw that in there. Factor of safety, if it comes up, it's just how much greater is the critical load over the allowable load. But here's the equation to keep in mind for this particular problem. Keep that one in mind. Any questions on that? Any questions on that? All right, thumbs up if we're good to go, at least understanding what concepts we need to go back in and review and make sure we understand. Thumbs up, appreciate y'all. Cool. All right, quick announcements. The goal is to have your latest grades back to you tonight, so you all can look at it. That is the goal. Hopefully it doesn't spill over into the morning, but nevertheless, you definitely should have it when you get to Sunday. But the goal is to have it to you tonight. Quiz 4, exam 2, working on that. Was out of town and busy earlier this week. Secondly, as you already know, we're going to drop your 3 lowest homeworks. So your homework grades, provided that you all did them all, should be better than they look right now. I think I don't know if we dropped them already, but we'll drop your 3 lowest and average your top without those 3. And then another breaking announcement that I hadn't said before, we will also go with your top 3 quizzes. So we'll go with your top 3 quizzes and we'll average those for your quiz grade. So if you missed a quiz, some people may have missed a quiz, or some people may have just really bombed one. So we're going to drop your lowest quiz grade as well. Let's see. I think that is all my announcements. When you get your quiz grades back, and once you get your final grades back, you are welcome to, between now and Tuesday, all right, whether as a final, before the final, take a look at Moodle and make sure it looks accurate to you. So if you want to see, just to check and see, hey, is this the same value, or this number correct based on what I see over here? If you see any discrepancy, if you're like you turned in something, or anything like that, you can give me an email. Usually not many discrepancies, but I do want to give you all an opportunity, if you look at your grades on Moodle by Tuesday at the latest, the day of the final, and you notice any issue, you can email me, prove, hey, I submitted this here, or whatever the case may be, and we can make sure that that's correct. And as you can see, there's no chapter 11 on the final. We touched on that for a quick second, but I told you we weren't really going to do that. So that is really all I have in terms of announcements. It's all I have for this review. I really appreciate y'all hanging out with me. This is definitely the longest video. It's going to be the longest video for people watching it on replay. But hey, class is really scheduled for an hour and a half. So we've been able to get away with shorter lectures than a full time. And that's mainly because we haven't had like Q&A going on throughout it. But I was really happy to do this because I know sometimes Q&A is needed in the middle of explanation. So any feedback, any feedback, feel free to speak up now before we close this out. And I'll probably put those announcements in the body of an email to everybody, just in case somebody doesn't make it to the end of this video to catch that. We're going to drop the lowest quiz grade too.
I have a quick question about the last lecture video that was uploaded.
Mm-hmm.
In the second problem from that video,
Mm-hmm.
you calculated I as pi r to the 4th over 4, when I'm pretty sure it's pi r to the 4th over 2. Or I assumed it would be. Was that just a mistake, or is there some reason why it was over 4?
It could be a mistake. It was a circular one, right?
Yeah.
Let me go back and look at that.
Yeah.
Yeah, I'll go back and look at that. I probably wrote R when I should have wrote D or something like that.
I I think it was probably just confusion because you did the area right before that, and that's over 4.
Okay.
But I wanted to make sure
have
of
made
it
a-
because it's
Okay.
the same type of problem that's on the homework tonight.
I will conclude that in an email, a follow email
All right.
right after this if I made an issue, if I made a mistake there.
All right.
Cool. Thank you, man. Any other questions? Pretty good. Do you feel like you've learned a few things? If it was in person, of course, I definitely would be asking this. You feel like you learned a few things in mechanics and materials? Everybody's good? All right. Cool. All right. Well, thank you all. It's been a pleasure being your virtual instructor. If you ever see me on campus, say what's up. All right. I'll catch y'all later.
Thank you.
No problem.